So hi everyone, my name is Tereza and I'm a first year PhD student in the membrane protein lab joined with EBIC and the University of Oxford. And and today I'd like to share with you my experience with the HexAuFoil grids from the perspective of small membrane proteins. So the talk will focus on a protein that I worked on during my year in industry, when I worked in the MPL and EBIC, and now it's become my PhD that I started in October. So the small membrane protein is 58 kilodaltons with very limited density outside of the membrane, making it quite a difficult target to work on. And all crystallization attempts were unsuccessful before, so we had AlphaFold prediction, but no real evidence, or we didn't know what the protein actually looked like. And so going into cryo-EM, we also struggled at the beginning to align the particles as, just because of no external density, just optimization of the data collections, buffers, nothing was helping. This issue was solved by getting a binding partner in the form of 15 kilodalton nanobody, which is an antibody fragment derived from llamas. And the nanobody stabilized the protein and added a density outside of the micelle or a nanodisk. And that was absolutely critical for particle alignment. And so when we look at the actual results we got with the protein, when I started working on it, we started with standard Quantifoils 1.2, 1.3, which are the most common grid type for membrane proteins under 100 kilodaltons. And using this grid type, we were able to get 4.2 angstrom resolution of the membrane protein. The protein was reconstituted into nanodisks and needed the nanobody to align the particles. This structure, however, came at the cost of needing, we collected over 113,000 micrographs. Yes, it was a lot, but I have to say the final 45,000 were actually not needed, as the resolution did not get improved by this, but we didn't know until we collected it. Any fewer than 300,000 particles in the final map deteriorated the resolution. But we were still very excited by the structure. Then this was all done during my placement, and when I started my PhD, my supervisor suggested HexAuFoils as a new promising thing. And I was a little bit skeptical, as the protein has previously shown a very strong preference, or more like a hatred, to majority of grid types. And so I managed to optimize the Quantifoil preparation. So it felt more like wasting the protein on a new, different, unknown grid type, but I couldn't have been more wrong. And very easily we were able to get 3.3 angstrom resolution structure of the protein from the HexAuFoil grid. This was a point mutant, so maybe people might suggest it's stabilizing mutation, but no, it's meant to be it's based on biophysical analysis, it's destabilizing, but the protein was prepared in the same way in nanodisks with the nanobody. So we kind of take them as equal samples with the wild type. And from just collecting under 36,000 micrographs, we were able to get to the resolution with 113,000 particles in the final reconstruction. So this was very unexpected, but actually very easy structure to get, and made us very excited about HexAuFoils. But when we compare the two structures in regards to other membrane proteins solved by cryo-EM that are under 100 kilodaltons, so kind of the edge, the edge of current cryo-EM possibilities, you can see that the structures aren't doing too bad. The protein isn't the smallest one when we take the nanobody size into consideration as well, but you can see that in terms of resolution, the HexAuFoil grids are doing much better, but they're not above the average. The same thing with the number of final particles in the map. Again, we were able to move it from needing 300,000 to just above 100,000. But again, these are very standard numbers for membrane proteins in this category. But the biggest difference comes when we look at the number of movies required, where even if I plotted the 80,000, this is quite literally off the charts. And it just shows how much the HexAuFoil grid helped with the protein. So yeah. But when we go back to beginnings and look through the process that was needed to get to the structures, there are some subtle differences needed or to be taken into consideration compared to standard quantifoils, such as the grid preparation. So in terms of Vitrobot settings, the recommended settings are blot times 5 and force 10, and that indeed led to very nice, thin, even ice throughout the grid and evenly distributed particles throughout the grid. And at 2 mg per mil, my protein and nanodiscs was maybe a little bit too crowded in the holes, but very usable, and this is the grid that we got the structure from. As an interesting point of view, or fail, depends how you look at it. One day I completely forgot that I was meant to change the settings and use my Quantifoil blotting settings at blot times 3, force 3, and even though we didn't measure the ice thickness precisely, you can see that the ice looks much thicker and you get much higher particle density. But the grid was still usable, and I got some initial model data from it as well. But when we look at the ice quality in general, compared to standard quantifoils, you just get much more even layer of the ice. My protein made on standard quantifoils very much preferred very thin ice, like at the point where you are questioning your sanity if there actually is any ice. But that was where my protein was, so it kind of makes sense that it very much liked the thin ice of the HexAuFoils. And another maybe side benefit to the HexAuFoils that I've experienced, they're much more sturdy than standard quantifoils, as confirmed by my notes, where initially I thought I completely smashed the grid and was reluctant to even put any protein sample on it. I did vitrify the protein on it. Ultimately, the grid turned out to be good, and I then ended up collecting on it. So I'm very big fan of this side benefit to HexAuFoils. In terms of data collection, there are again a few subtle differences compared to the quantifoils. So they follow the same rules, except for needing to do autofunctions on a carbon grid. So you always need to have that one around. And you can use much lower defocus on the gridsquare and hole magnification. And I've had good success with repeating image shift calibrations to help with the hole targeting in EPU data collection, which goes in hand with determining the hole size, which it seems sometimes when I choose the hole size a bit too small or a bit too big, the hole targeting accuracy decreases. But if that is the case, I tend to go back to image shift calibrations, tweak the hole size, and that seems to help a lot. We have also done a 30-degree tilted collection on HexAuFoils, which again follows the same points as I mentioned before. And on top of that, we have changed the image beam shift from 12 microns to 6, which helped with the hole targeting. And again, repeating image shift calibrations and tweaking the hole size, and we were able to get really accurate hole targeting. And how accurate, if you ask? If we look at when you have a collected image, and if you think of like a center of the hole and how far offset it is from the center of the data acquisition image, you can see that it seems that the 30-degree tilted data collection is actually performing better than the untilted one. There is probably very easy explanation to this. Well, the IBS has been changed to 6 microns. The AFIS calibrations on the Krios 4 were done literally the day before we collected this data, so they were spot on. But probably the biggest difference is that the Krios 2 untilted data collection was our very first HexAuFoil data collection, and at that time we weren't absolutely sure how accurate the hole targeting actually would be. So we were willing to tolerate imperfections. But even if you look at the red holes, they are offset by 30 to 40 nanometers. That is still, you're hitting 70 to 80% of your holes, so you're still getting very valuable information from each of the data collections and data acquisitions. So it's actually not that bad, and we think we can very much improve this. But this just confirms that tilted collection is very possible and reasonably easy to do on HexAuFoils. Yeah, that's just the distribution. We have also collected on 200 kV microscope Glacios, and again, the same rules apply, except for the need, or the issue with large illuminated area. So you need to skip holes. You cannot collect on every hole. So you're not pre-exposing your holes, except for the auto functions for this each AFIS group. But other than that, I was able to get really nice data from just a small scale Glacios data collection. So again, very easy to do. In terms of data processing, I have not found or encountered many issues with the HexAuFoil datasets. The only thing I can think of is potentially particle picking. So I will go through the different softwares I used. Quantifoil is the first software that is used in EBIC, as EBIC has an automated processing pipeline that runs on Reliant 4 and uses Quantifoil for particle picking. The particle picking isn't perfect, but can be optimized by downstream manual tweaking of the settings. I have also tried to use Reliant, but I have to say I did not try too hard, as I'm unable to properly align the particles in Reliant of my membrane protein. This is not an issue with the HexAuFoil grids. I have had this issue with Quantifoils before. It's just that Reliant and my membrane protein seem to not be compatible. But I gave Reliant a go with the new HexAuFoils, and I have managed to optimize most of them. I have not tried too hard with the topaz, I have to say. But yeah, it takes a bit of time to optimize the picking and the thresholds, but it's absolutely plausible. But CryoSpark is my go-to processing software, and the particle picking is actually really nice and easy to do, as WobPicker does a really good job. And if followed by inspect pick job, you're able to remove majority of unwanted picks, and I have not had issues with using CryoSpark and HexAuFoils. And actually both of the structures you saw at the beginning were solved in CryoSpark. So ultimately, are HexAuFoils the future for small membrane proteins? Who knows, maybe. And even though there might be possibly some issues with particle picking, you can very easily do a tilted collection if your sample requires it. And the blotting settings are very forgiving. And you get very high reproducibility of grid quality and ice throughout the grid. And ultimately, this meant that I was able to get an angstrom improvement in resolution of my small membrane protein from the HexAuFoil grids. And with this, I would like to thank everyone from the Membrane Protein Lab and EBIC, and especially Peter Harrison, who's one of my supervisors and who's taught me everything about cryo-EM and HexAuFoils. And this talk would not be possible without him. So thank you for listening.